Okay, so this leads us to the larger questions of exploration versus exploitation. When should we explore and when should we exploit for more knowledge? When should we explore for more knowledge or exploit our current knowledge? And this can be thought of as short-term versus long-term planning. Of course, if we want to plan more to the long term, we would like to acquire more knowledge. If we would like to plan for a shorter horizon, we would like to mainly exploit our current knowledge. And so this raises some questions, but let's look at a simple example. So let's say, for instance, you have two options for lunch. You have the usual place, so this is a place that's been open for a long time, right? It has pretty good reviews, 4.2 out of 5 stars, and many people have reviewed that already, so one might say that this is a pretty high confident review. However, the new place has a bit of a lower score, but it's newer and less people have rated it. So you might say that you're less confident about the current score that this restaurant is assigned. So what would you have chosen? Where would you like to go to lunch?
Well, although I love my usual place, I love to explore. And I don't know if I can trust just 7 ratings. Maybe I want to explore the new place. It does look pretty fancy.
But your decision is dependent on more than that, right?
It's also dependent on the ratings, I guess.
And the knowledge that you're going to gain from going to the new place, well, it might help you, but it won't help you today, right? Mm-hmm. So there's also a question if you're in a new city, for instance, and it's you're just going for lunch today, and the knowledge won't help you later on, then maybe you'd actually prefer to go to the usual place, right? So this is a function of your optimal decision is a function of, first of all, how confident you are regarding the current knowledge, but also regarding the short versus long-term planning, if you're going to repeat the same action over and over again, or in other words, how beneficial this new knowledge will be to you. Are you willing to sacrifice some gains in today's lunch for better knowledge for future gains, for future lunches?
Or if I want to save my money, maybe the new place is too expensive.
Maybe, you know what, but we'll just include that in the reward function.
Yeah.
Okay, so the score here includes the value for money, let's say, in this case. Okay, so as we saw, the decision whether to explore or exploit it depends on several stuff like uncertainty, planning horizon, and how confident you are in the current estimation. So in order to address this trade-off, we're going to discuss several exploration versus exploitation strategies. We'll have to make several assumptions. So for now, we're going to assume that our estimation, our Q estimation, or our expected reward estimation is we have a very simple evaluation function, which is just the average of the rewards that we saw so far for choosing a specific action. And of course, we'll also need to define what happens, what is our estimation for an action that we never tried before. And let's just say that we assign it with a constant value, which is just 0. And then the question is, after some t time steps, what would be the action we should choose next? So as we've seen before, we can always choose the greedy action. We can set that as our strategy. Okay, that is, we'll choose the action with the maximal current estimation, the maximal Q estimation. This allows us to exploit our current knowledge and to probably maximize our immediate reward. So this might be relevant if you're looking for a lunch in a city and you're flying out tomorrow and you say, hey, I don't care about exploring, I just want to maximize my current reward, right? But someone might say that this is a short-sighted strategy, so if you're staying in this city, maybe you should actually try new places and gain more knowledge. Because this will, if you just follow the greedy action over and over again, it will prohibit you, or it will not allow you to discover more lucrative actions if such exist. Right? So let's discuss a simple exploration strategy. This is known as the epsilon greedy exploration strategy. By the way, it's a very simple one, but it is still commonly used in our algorithms these days. Although more sophisticated techniques do exist, but we'll discuss them later on. Let's start with a simple one, the basic one. So epsilon greedy means that with some probability, epsilon, that we define, this is a hyperparameter, this is something that the user provides to the RL agent. Okay, this is known as a hyperparameter. We'll discuss the difference between a hyperparameter and a parameter later on. But the epsilon would be a hyperparameter. You can set it, for instance, to 0.05, and with a probability of 1 minus epsilon, so with a high probability, you will choose the greedy action, else you're going to choose a random action. Yeah, a completely random action. And so this has some nice theoretical guarantees where it will guarantee that all of the actions will be sampled infinitely often. And later on I'll give you a mathematical definition of infinitely often. But for now you can just think of that as at infinity you will sample each one of the actions infinite amount of times. So there's no point in time where you'll stop seeing action from that point onwards. Okay, you'll always visit with some probability any of the actions in your action space. And so the nice thing about this, about guaranteeing infinite often visitation or sampling, infinite often sampling, is that the Q values for each one of the actions is guaranteed to converge at the limit to the true Q star values, to the true expected reward. Okay, so let's see how this exploration strategy actually performs in a simplified scenario. So let's say we have 10 different bandits, right? One on bandits. So, and each one of these bandits, so this is, we have k equal 10. And so your action space is playing one of these machines at each time step. And the reward probability, the reward distribution from playing each one of these machines is provided as a Gaussian with a specific mean, which is your Q star, because since this is a Gaussian, the expected outcome is the mean, is the mu in this case. So the mean is given here as Q star, and you have one standard deviation for each one of these machines. Okay, so the reward is not deterministic, it is drawn from this distribution, but still you can see that it's probably best to play, which action is the best here? 3, right? Yeah.
Or 5. No, 3, yes.
No, 3 is a bit higher than 5.
You're right.
Okay. So 3, playing machine number 3 is your best, is the best policy, is the optimal policy. However, you might play machine 3 and machine, 4, and in a single sample, it might be the case that machine 4 provided you with a higher reward, right? And this is why you don't want to converge prematurely on your optimal policy, but you always want to sample the different machines just to see that just to guarantee that your estimation regarding the Q star value eventually converges on the true value. Okay, so as written here, the optimal policy is to always choose A3, but we don't know that initially, so we have to learn through interactions. So let's see some results. So the results here shows you on the x-axis you see the steps, so how many times you already tried one of the actions, and the y-axis is the average rewards, and the different curves shows you different epsilon strategy exploration techniques. Okay, so you have epsilon equals to 0, that is, you always play the greedy action that you know so far. Then you have an epsilon of 0.1, so with probability 0.1, you choose a random action, and with probability 0.9, you choose the greedy action, actually a bit higher than the 0.9. So also if you choose the, if you go random, there is still a probability of choosing the greedy one.
That's true.
So actually choosing the greedy one is the greedy action is a bit higher than 0.9. And then you have an epsilon of 0.01. And these curves present the averages over 2,000 runs, each with 1,000 steps. All methods use sample averages as their action value estimation.
Professor, what happens if we increase epsilon further?
So one second, I'll just finish describing the results. So actually on top here we have the y-axis as the average reward, but on the bottom here it's kind of a similar curves, however they're less noisy because they're showing you the percentage of optimal action. That is the percentage of time you chose action number 3. So this is a bit less noisy because for choosing a specific action, here on top you can see that you still have a very noisy outcome because of the distribution of other rewards. So what was your question? If we chose a very high epsilon?
Yes.
Okay, so let's look at the result and we'll try to estimate what will happen if, how should the curve look for a higher epsilon. Okay, so what do we actually see here? So let's look at the first results here on top. We see that an epsilon of 0.1, that is one that favors exploration, actually converges or learns. It actually learns much quicker compared to those with the curve with a lower epsilon, an epsilon for instance of 0.01. An epsilon of 0.01 still learns, but the learning is slower, right? And that makes sense because it explores less. And you can see that with an epsilon of 0, you quickly converge on some performance, but that performance is suboptimal. So you don't, very quickly you stop learning. You don't see any learning for this curve. By the way, when I say you see learning, how do you see actually that one of these curves is performing learning, is actually learning?
I see that it gets a higher average rewards quicker.
Over time, right.
Yes.
So the slope would represent the amount of learning, right?
Yes.
So you can see a higher slope for the black curve, for instance, meaning that it learns faster. Okay? And we can see kind of similar results. We can see kind of similar results when we look at the percentage of the optimal action. However, these are a bit less noisy, right? But the results are similar. Now, that was a good question. What would happen if we set a much higher epsilon? What would you accept? Or what would you expect?
Well, looking at these trends, I'd expect it to converge even faster.
To learn even faster? Well, so let's say we have an epsilon of 0.9. What would you expect to happen?
Well,
how will you draw?
I guess I'd expect it to go even faster like that.
Well, but then with an epsilon of 0.9, you're right that you'll converge or you'll learn the Q star values quicker because you sample all of the action space and you might converge on Q stars even quicker. But that won't necessarily be the case for the greedy action, right? So you're actually sampling all of the action space almost uniformly. Specifically, if you have an epsilon of 1, well, you're just sampling them uniformly. And the issue with that is, let's say you set epsilon to equal 1. What curve would you expect here? Let's say the percentage of optimal performance, of optimal action?
Well, it's completely random, so I would.
So it will be here, right?
Yes,
It will
very
be
low.
0.1.
Yes.
Right. So acting completely random will gain you maybe important information, but you won't act optimally.
Mm-hmm.
So we always want to balance between sampling or exploring the action space, but also starting to converge on the optimal action. Okay? And now I have a different question for you, which is, so by looking at these results, what would you say is better? An epsilon of 0.1 or an epsilon of 0.01?
An epsilon of 0.1.
That seems to be the case, right? It's dominating, I would say,
Yes.
the learning curve for epsilon 0.01. But what would have happened if we continue this this learning process? Okay, so let's say. So, what would you expect to happen if we continue this learning with respect to the red and black curve?
Well, they did find a good policy, but I guess they're still exploring quite a bit. So they would continue to collect more samples?
Yes, no, I'm asking about the curves. So currently we see that the black curve dominates, right? Higher is better?
Yes.
It dominates the red curves. Do you expect this trend to continue? So let's say at infinity.
At infinity, I'd say they would perform about the same.
About the same?
Yes.
That's interesting.
If they found the optimal policy, but I guess that depends on, like you said,
so,
exploration.
As I said, right, you still have some random exploration. So both of these are guaranteed. Of course, that's not true for the green line, but both with a probability of 0.1 and probability of 0.01, you're guaranteed to have infinite often sampling of the action space, because you have some probability. At infinity, you'll sample all of the action space infinitely often. But if we look at the percentage of optimal actions, what will the black line converge on, and what will the red line converge on? That's my question.
I guess.
So as you at infinity, you learned, you know the optimal value, you know Q star, right? You converge on Q star. What will these curves look like? What will they converge to?
I would expect epsilon 0.01, the red line, to actually have higher number of optimal actions than the epsilon 0.1, because even after they
Can you give me a value?
A value, it'll be 10% more. Right? I guess.
So the red line should converge on, it knows the greedy action.
Oh, that should be 100%. The
0.01? You still have some.
Optimal action for epsilon 0.01 would actually not be 100%, it'd be 0.99, I guess.
It will be 0.99
or a little more,
a bit more, right? Because
yes.
With a random action, you still might.
For 0.1, it'd be 0.9.
It will be 0.9, right?
Yes.
Okay. So the black line should converge on 0.9 plus a bit, right? As we said before. So this should be the black one, and the red one should converge on something more, a bit larger than 0.99. So we would expect the trend that we see here, where the black line dominates the red line. We know that this won't stick if we continue this learning to infinity, right? Mm-hmm. At some point they will switch. Now you can say, well, yeah, but this can be easily solved, right? You can say, well, I can start with a high epsilon just to gain initial fast learning, and then over time I'll decay epsilon, and then I'll get the good asymptotic performance. Yes, okay, so again, epsilon greedy is a pretty common, still these days it's basic, but it's still very common exploration strategy, and indeed, in most cases, and in most algorithms, we decay the epsilon. So we start with maybe a high epsilon, like 0.1, and decay it over time. Okay, and we'll see that later on.